Hello, my name's Tom, and I am going to be taking you on a detailed course through the wonderful world of custom LED engineering. So I put together a little presentation, and we're going to walk through it. It's going to be quite a ride. We're going to go into some excruciating detail and hopefully motivate you guys to give this superb hobby a whirl at some point. So, custom LED engineering for stages, installations, and wearables. We'll get down into the details of what those mean in a minute. I'm going to introduce the table of contents here of what we're going to be going over, just so you guys can have a flavor of what's going to be happening. And maybe you can skip forward to the items that you care most deeply about, or use them as future reference as you're trying to build your first project. So I'm going to do an intro. The purpose of this is mainly to show you some stuff, show you what we're talking about, show you some completed projects, and motivate you a little bit. Then we're going to start talking about types of lighting and why LEDs and the types of LEDs I work with are different from other commercial conventional types of lighting that you might encounter in the wonderful world of lighting engineering writ large. Then we're going to talk about different types of project. So what's the difference between a wearable, this is a wearable, versus an installation, which might be a standalone sculpture or something like that, versus a stage, which is probably the highest level of complexity of LED project, because it's very time constrained. There's going to be performers on the stage. You need to interact with a lot of other pesky humans. Humans always cause problems. Lots of other moving parts, lots of stuff to consider. So those are the types of projects you might have the fortune of working on in your hobby as an LED engineer. Then we're going to get into the technical stuff. So concepts in lighting, some overarching concepts that we're going to need to start establishing the technical language of how we talk about these things. And ultimately, the objective there is to arm you guys with enough knowledge to go and search out additional sources, additional resources to provide you with guidance along your journey. Then we'll go one level deeper into the specifics, the technical specifics of LEDs and the actual physical components that are required to do LED engineering. Then we're going to talk about electronics, of course. LEDs are electronic devices, and you won't get anywhere unless you know a little bit about electricity, electronics, and circuit design. Then we will have a review of control engineering, which is probably the most complicated and most challenging section of this. Totally required, but the headline here is: how do you tell these wonderful LEDs that can change any color to do what you want them to do? How do you control them? And then finally, we'll talk about some of the auxiliary components that are required for an LED project, such as the substructure. So what are the LEDs on? Are they on a leather strap with some feathers attached to it? Or are they on a bog standard truss that you would find on a stage anywhere in the world? Or are they on something completely custom built? Or are they on a camel for one reason or another? And then the final concept will be diffusion, which is the simple art of taking light and adding a barrier between the light source and the viewer that disrupts the light or spreads it out or changes the flow of the light in some way to give it a different visual effect. So that thing on the side looks a little bit milkier, looks a little bit juicier. that's an example of diffusion, which we can get into later. So that concludes the table of contents section of this seminar. So the next phase is to just show you a video of my favorite project that I've ever worked on, and we can talk through some of the elements. Okay, here we go with the video. Sound off. Now you can find this on YouTube if you search for the right thing. The thing you'll need to search for is Hooligan Alley 2019. You'll find that in the top left corner. So what on earth are we looking at? You're looking at a flying hexagonal grid composed entirely of LED bars. Here you can see us constructing the substructure. So this is a conventional stage truss. And here you can see us time-lapsed hoisting the LED hexagonal grid up into the air. And here it's party time. So you can see people milling about. You can see a box sort of to the left underneath one of the legs of the truss. That's where our control is taking place. This is a view from behind the DJ booth. That big blast of light is some pyrotechnics, which is another wonderful subject that unfortunately won't be covered within the scope of this seminar, but there you go. And most importantly, there are our beautiful LEDs. So changing all sorts of different colors, going in time with the music, being really, really well coordinated with one another, changing the theme, establishing the mood, speeding up the tempo, slowing down the tempo, getting more frantic and granular, or having smooth, gentle color washes, mixing between scenes, basically getting the crowd amped up, which is the most exciting thing and the most rewarding thing in the hobby. And here you can see that even in the daytime, or at least at dawn, you get some pretty decent lighting effects there. So that is just an initial overview of one of the projects that I've worked on. Hopefully that gets the juices flowing a little bit. And moving on to the next section. Hello again, guys. Sorry for the interruption. I just had to change my headdress. The other one wasn't bright enough. But I'd like to give you a quick tour of this one so we can establish some concepts. So what do you see besides an idiot wearing a silly hat? If you look in really close, and I zoom this directly into the camera, you will see our LEDs, our light emitting diodes. These are individual little surface mount light emitting diodes in triplets, red, green, blue triplets, attached to a printed circuit board that allows power and control circuitry to be delivered to each LED. Maybe you can get some detail if we go in really close, maybe not. We've also got a couple of other elements here. We've got substructure. In this case, it's a ram's horn, nice padded sheepskin headpiece with some wire frame. There are, of course, a multitude of feathers. Those are just for decoration. They're actually not functional feathers. And then if we look into the guts of this thing, we have some control circuitry. So control is a big subject. We'll get into that a bit later, but that is essentially the brains of the headdress telling the LEDs what to do. And then this micro USB cable that is entering the circuit is our source of power, with this leading out to a conventional 5-volt DC cell phone battery pack. So I'd like you to sort of keep those various concepts of what goes into a headdress in your mind as we go through this demo, and I will keep them on my head. Now, I'm just gonna, we've had a demo of a stage. That was the video I showed. We've now had a demo of a headdress, also known as a wearable. You could wear this headdress, on your foot if you wanted to. Let's just quickly talk about an installation, just because I think it's a great opportunity to show what I think is the best installation I've ever seen. And it's a piece called Radiolumia, which was made by a group called Fold House. So let me share my screen. So you might notice a couple of similar production, there's a production phase with some similar mechanisms and a similar backdrop taking place. These guys are absolute pros. So think about the same elements we've been discussing. You see substructure, you see LED bars. There's obviously some very serious power circuitry and control circuitry taking place. But yeah, Radiolumia by Fold House, one of the most superb pieces of art I've ever seen in any context. And look, they've even got a kinetic element. So it moves and it breathes. So this is basically the pinnacle. This is what we should all aspire to be able to achieve. And hopefully this course is a small step in the right direction. Okay, let's bring it back to the presentation now. So we've talked about a headdress, we've seen an installation. I just want to reiterate that this is an introductory course to point you in the right direction, okay? So you're not gonna get everything you need from this course, but hopefully it will motivate you and get you moving. This is a very rewarding hobby. So ultimately, the theory you learn here can only take you so far, but like the headline has got to be you have to just do it. Get stuck in, buy some LEDs, buy some circuitry, start messing around with it, start learning. The best way to learn is by doing. Okay, so let's dig a little bit deeper into different types of lighting you might encounter in your quest to become a custom LED engineer. So first, let's go through some conventional lighting types that are not what we're going to be talking about so that you can learn to distinguish them. So we are not going to be talking about stage blinders. What are stage blinders? Let's have a look. So stage blinders are very powerful, sometimes incandescent bulbs, sometimes LED-based spotlights that are essentially unidirectional. They shine directly out of the stage. They give you a very sort of rock and roll effect. And they can just pulse on, usually monochromatic, so they only do one color. They just blast the audience with light, okay? This is a conventional lighting asset that a lighting director might use on a stage. And we are not going to be talking about stage blinders. Parkans. What's a parkan? Well, a parkan is very similar to a stage blinder. Par is short for parabolic, okay? So it's a parabolic reflector. That means that you essentially have a bunch of lights, and at least historically, behind them, you've got a mirror in the shape of a parabola. So sort of like a concave mirror or a convex mirror, which serves to bounce back any light that travels backwards into the casing of the light fixture, and focus it so that it comes outwards and hits the eye of the onlooker. So that's historically why they're called parabolic cans or parkans. Nowadays, they don't typically actually have parabolic reflectors in them. This one appears to. There's your parabolic set of mirrors with an LED fixture in the middle. But something like this looks like it probably doesn't have any actual parabolic mirrors taking place. Now, these are another conventional lighting asset that you may encounter in your travels that a lighting director might use. And although they contain LEDs, this is not what we're going to be talking about in this seminar. Okay, spotlights and moving heads. What are those? Well, in many ways, they are an evolution of the parcan. So these bad boys are, this one looks like a parcan, but it's got this multi-axis kinetic mechanism, which allows you to point it in different directions in real time. So you can sweep the light across a stage, across the audience, point it in different directions. Some of them have very powerful lenses on the front, so you can make that beam really focused and nice and tight. You definitely will have encountered these moving head or spotlight lights. So if we have an example of the best in class, hey, look, free advertising for YouTube. When you see something like this, like each one of those is sourcing from an individual moving head spotlight. Very exciting, very related to what we're going to be talking about, but not exactly what we're going to be talking about. And finally, lasers. So we all know what lasers look like. Let's just reiterate. Lasers are objectively awesome. They have the narrowest beam of light of all, the most concentrated light, the most luminous intensity, which is the amount of photons that travel through a unit surface area per unit time. These are actually powered by LEDs. So the source of light inside these lasers is originally an LED, but it gets amplified by some science, which is beyond the scope of this seminar. And we all agree that lasers are awesome, but lasers are also not what we're going to be discussing in this course. What we will be discussing in this course are custom LEDs, okay? Custom light emitting diodes. So what this means is buying base components, so essentially raw materials, electrical circuits, and using them to create your own lighting fixture that you design all the way from scratch. Okay, so these are not off-the-shelf products, which means there's a lot more work required and it's a lot more difficult. However, if you build a custom LED installation, wearable or stage, it will be totally unique. No one else will have anything like it. And it will be all the more rewarding because of that. All right, let's get down into the details of LEDs. So what is an LED? Well, LED stands for light emitting diode. Now, there's a lot of theory we could get into here, but ultimately what you need to understand is it is an electronic device which takes electricity or electrical potential energy and converts it into light. Now, if you were to look at the Wikipedia page, there's a lot of physics detail here, but ultimately it is a light source that emits light when current flows through it, okay? And if you were to ever see an LED on an electronic circuitry formal diagram, this would be the symbol, okay? Now, diode implies that you only want your current to, it will only permit current to flow in one direction. So they do have a polarity to them. So when you put LEDs into a circuit, they will need to be aligned in the correct way. So just something to keep in mind. Now, let's talk about some characteristics of LEDs. The first thing that I would like to draw your attention to is that these things you see on my hat, when you buy that as a part, it's more than just an LED. The light you're seeing originates from a light emitting diode, lots of light emitting diodes, hundreds of light emitting diodes actually. But when we buy LEDs, the base materials, we're buying a printed circuit board with LEDs surface mounted to it and other circuitry, okay? So to distinguish between what this is and the LEDs themselves, we're going to introduce the term emitters. So what I've got here is a whiteboard with a diagram of a zoomed in version of what's on these LED strips inside my hat, okay? And I'm going to walk through this diagram. This is going to be the basis of how we talk about the different components associated with LEDs or LED strips, okay? So the first concept is an emitter. The emitter is actually only a small part of the circuit board here. This R box, the G box, and the B box, those are emitters, okay? Now, I'll do a brief overview of why we want an R, a G, and a B, a red, a green, and a blue here, together in one unit. And we'll get deeper into the color theory later. But ultimately, in order to express any of the multitude of colors that we can perceive as humans with our eyes, you can accomplish a lot of that by combining red, green, and blue light in different amounts in order to produce other colors. So the way these chips work, the way these emitters work, is it's a set of a red, a green, and a blue emitter in one package. Okay, let's see if I can give a demo of this. So if I turn this off and zoom in really close, you might be able to start seeing that circle in the center of that white square. That circle actually contains those three emitters. They're almost too small to see with the naked eye, but they can produce an enormous amount of light. One moment, I have to turn this back on because I just can't speak without it. There we go. Okay. So emitters, they are the source of the actual photons that you see. Now, let's talk about formats, okay? So what do I mean by format? Now, a lot of this terminology is stuff that you'll need to know when you go out into the wild and buy your LED components for the first time. And the main one that you need to understand and watch out for and look for is SMD 50/50. Okay, so what does this mean? So from what I've gathered so far, SMD means surface mount. That means that that square package with this circle in it that you just saw is mounted to the surface of a printed circuit board. So a pick and place machine, which is a robot, typically in China, in Shenzhen, China, where a lot of these things are manufactured, will take these little surface mount components, those square packages, place them onto a printed circuit board, apply some solder paste, which will ultimately melt and fuse the connections between the input pins on this surface mount component to the printed circuit board so that the circuit can be completed and used. And then pass it through a reflux machine, or basically an oven, which will melt the solder paste and complete that circuit. Okay, so SMD 50/50, we know what surface mount means. What's the 50/50? Well, that's simply the size. So 50 50 means 5 millimeters by 5 millimeters, okay? This is the most typical form factor you'll find in surface mount emitter packages. And yeah, it's pretty much ubiquitous. There are other form factors. There are smaller ones. I think there are 35, so 3.5 millimeters by 3.5 millimeters. And there are some other ones, but the most widely supported are SMD 5050. Later on, when we get into an example of how you buy these things, we'll show an example of this. So the next concept I want to introduce, and this is possibly the most important one, is this concept of addressable versus dumb LEDs. Now, if you look at this hat, you'll see that at any given moment, especially when the animation gets nice and exciting, which it isn't right now, each and every LED has the capability to be a different color to its neighbors at any given time. So this emitter can show a slightly different color or a vastly different color compared to this one, compared to this one, compared to this one. What this means is that from a circuit perspective, and also from a software and control perspective, each of those emitters has a different address, okay? So you can call it up by its address and tell it to be a specific color at a specific time, emit a specific color at a specific time. Now, the alternative here is, well, there isn't really a good word for it, but we typically call them dumb LEDs. A dumb LED strip is not addressable. So that means that it doesn't have the capability for adjacent LEDs or any of the LEDs, any of the emitters, to show different colors at different times or at the same time. What this means is you can't ever hope to create any of the complex animations that you're seeing on this hat with dumb LEDs. So addressable is a key consideration here. You want to be working with addressable LEDs unless you have a particular use case for dumb LEDs. Now, what is it that makes LEDs in a strip or on a printed circuit board addressable? Okay, how on earth could these little chips that exist in a circuit understand that they're different from one another? So each of these emitters has an integrated circuit associated with it. It's got a little, essentially something like a logic circuit or a microcontroller associated with it, which is what gives it its address. So you will see this referred to as IC. So what IC, which stands for integrated circuit, are these LEDs operating? And so when we go into an example of purchasing LEDs, you'll be able to see the different ICs that are available. Sometimes it's just referred to as chip, okay? So what is the chip? Now, the way these things work is when you send a signal to your LEDs, which goes down a wire, it's a digital signal that goes down a wire, the IC will pick up the section of that signal that pertains to the LED at each address and react based on the part of the signal associated with that address. So that way you can send out a signal with all the colors that each of the LEDs needs to be, and each IC will detect the right part and set the LED to the right color at the right time. So two IC types to recognize and remember. These are the two most supported, most widely used, most conventionally found by hobbyists. They're good options to look for. The first is called WS2812B. It just rolls off the tongue, doesn't it? So WS stands for World Semi, which is, I think, a Taiwanese manufacturing company, and 2812B is sort of the part identifier. So this is essentially a depiction of a WS2812B printed circuit board. Okay, and another one is called APA 102C. There is a fundamental difference between these two, which we will talk about in the control section. But for now, just try to recognize and remember those numbers. Cool. And for the record, this hat is made using WS2812Bs and also the Hooligan Alley installation you saw at the beginning of this seminar was also made using WS2812Bs. Okay, let's talk about modules. So the concept of modules essentially means how many emitters are being controlled by each IC, okay? So we've got the concept of emitters, which is where the light actually comes from, and the concept of the chip, the IC, which gives those emitters their address. Now, what you're seeing in this hat is one emitter per address, okay? One emitter per IC. And that means that essentially you've got a pixel associated with an address. This doesn't have to be the case. You could have multiple pixels associated with a single address. And in fact, there are lots of different formats that these LEDs come in. So this is a strip. So you get essentially a linear arrangement of LEDs, emitters, each addressed by their own chip. But there is a lot of other stuff. And when I do an example of how to buy these, I'll show you some examples of other types of modules, and they can get pretty wacky. Now, related to this concept of modules is voltage. So in order to successfully construct any sort of LED installation or wearable, you're going to need to build an electronic circuit. And a defining characteristic of that electronic circuit is what voltage it operates on. You have to get the voltage right in order for the LEDs to work and for them to not burn out. So the operating voltage of this hat is 5 volts. 5 volts is very typical. 5 volts is the voltage that a lot of microcontrollers and control circuit boards run on. It's low voltage. It's never dangerous. You wouldn't even be able to feel it, even if you were being shocked with 5 volts, most likely. Lots of like your cell phone gets charged at 5 volts. This is a very, very universal conventional voltage. These operate at 5 volts. So you have to provide them with exactly 5 volt power. It's very nice to work in 5 volts because since if the LEDs run on 5 volts and your controller also run on 5 volts, then you can simply have one power source, one power circuit powering everything, and you don't need to worry about supporting multiple voltage levels in your system. 12 volts is another option. There are advantages to 12 volts, which we will describe when we come into the like electronics and power circuitry section. But typically what you'll see is that 12 volt LEDs have 3 emitters per module. Okay, so instead of 1, like here, you will have 3 emitters per module. So overall, more brightness, more luminous intensity per module, but lower resolution because those 3 pixels need to spread out. They need to occupy physical space. And so there will be more distance separating each address, which ultimately leads to lower resolution if you're trying to get something really detailed. So my advice is typically it depends on how far away you think the audience is going to be from the object that's covered in LEDs. For a wearable, I like 5 volt single emitter pixels. And for stages and installations, 12 volt and upwards of 12 volt can be great, okay? There are 24 volt LEDs. They have 6 24 volt pixel units, which have 6 emitters per module or 6 emitters per address. And just to review, that's one chip controlling 6 emitters all at the same time. That means every emitter inside that pixel has to be the same color as every other emitter at any given time. but they remain distinct from their neighbors and all the other emitters in the chain. Now, this brings us on to a closely related topic, which is the pitch or density of these LEDs. So pitch simply means the distance between emitters or modules. And the density is a related concept. So the less distance there is between emitters, the higher density they are. So as I said, typically you want to gauge what you need based on how far away you think the viewer will be. In the world of LED strips, there are two conventional densities which you can purchase. 60 per meter, which is this density, which is typically the highest you want to work with. You can get higher than that, like 72 or 144, but the power requirements for that quantity of LEDs become so high that the electrical engineering gets quite advanced, or at least, and at the very least, those wearables get very hot. And of course, the materials are more expensive as well. But if you can pull off a well-made, robust wearable using LEDs at 144 LEDs per meter, I will be seriously impressed, and it will look spectacular. It's just a challenge. So the other option is typically 30 LEDs per meter. So that would be half the resolution that you're seeing here, much less dense, also cheaper, slightly easier to repair. So there are trade-offs here. One other very very thing to think about when purchasing these units is the PCB color. So the PCB stands for printed circuit board. It's how it's the physical circuitry that underlies these things. So what these emitters are mounted to is called a PCB. You can get it in black or white. So you want to think about where you're installing these LEDs, what you're putting them on when you decide this. Do you want the printed circuit board to blend into the background? Are they going to be adhered to some painted structure? Would you rather have a white background which has the capacity to reflect some of the light and make it a little bit brighter? Or would you rather have a black background which is easier to conceal and makes the LEDs look more sort of streamlined or difficult to recognize as electronics? There are advantages to both. And yet another consideration is the IP rating. So this is essentially a waterproofing rating. This is like a universal standard in materials and products, is the IP rating. So a higher IP rating means more waterproof, more robust, more protected. LEDs come in a few different typical IP ratings. The best and most protected is IP67. So this means that the LED strip will come inside a silicon hose, essentially, which is a totally separate unit to the printed circuit board. So it's not physically attached, except for at certain locations. So this is very nice to work with because it's very easy to cut and remove if you need to. If you need to repair the LEDs, that's easy too. It also provides the highest amount of waterproofing. Now, the interesting thing about waterproofing is that's not the only type of protection you want for your LEDs. Obviously, it's very nice if you can set up your installation and know that if a thunderstorm strikes, nothing is going to go wrong. But there are other environmental factors which contribute to the wear and tear of LEDs. It's quite hard to build an LED installation already, and it's even harder to build it twice because there's typically some degradation of your materials, that just like people banging into them, the elements, etc. So things like dust and dirt can be just as bad for LEDs as water. And so the higher the IP rating, the better generally. There's a middle ground, which is IP65, which is essentially a silicon putty that's overlaid directly onto the printed circuit board, and it envelops and encases the emitters and all of the circuitry on the front, not on the back. So this is one step down in terms of protection. It's also a lot harder to work with. So if you want to remove this silicon putty in order to access the circuit board, in order to make a repair or do some soldering or splice two sections together, you will have to go to an extra step of scraping it off quite diligently with like a Stanley knife, for instance. And that creates a mess and it's time consuming. This hat happens to be the IP65 version. But ideally you want to be working with IP67. If you are lucky enough to have an installation that is going to be in a static protected location for a long period of time, like indoors in an art gallery, you can get away with working with what's essentially unprotected LEDs. So IP35, so even unprotected LEDs have an IP rating. And so these won't have any silicon piping, no silicon hose, no silicon putty. They do have a vaguely waterproof spray, which is a very standard finishing practice for printed circuit boards. So they will be like vaguely water resistant, but nothing I would trust in a thunderstorm. But that is an option. Okay, cool. Let's talk about how to actually acquire some of these LEDs, how to buy them. Essentially, what it comes down to is they're all manufactured in China. China is the world's leading manufacturer and exporter of these LED units of all shapes and sizes. I had the fortune the luck to get a chance to live in Shenzhen in China for 4 months. And they have an entire shopping mall. They've got multiple entire shopping malls on the high street just dedicated to LED components. So we're talking a 6-story building with 100 market stalls per floor just dedicated to LED components. So there are lots of options. If you don't live in China and you can't go to those markets, you've basically got 2 websites to work with: AliExpress and Banggood. These are both Chinese export websites for electronics and other stuff. So why don't we take some of our terms that we've just learned? We want SMD 5050. We want to choose an IC between WS2812B and APA 102C. We want to figure out what module type we want. We want to figure out what voltage we want. We want to get the right pixel density. We want to choose the color of our printed circuit board, and we want to choose an IP rating. So let's type some of these terms in and see what we get. Let's start with addressable. Got some options coming up. RGB 5V addressable WS2812B, that sounds promising. So what have we got? Lo and behold, we've got all sorts of different suppliers selling these strips. So if we go into one of these, let's see all the different options. So this is a supplier selling exactly this, WS2812B strips. You can buy them in 1 meter, 2 meter, 4 meter, or 5 meter lengths. I definitely don't want notifications from AliExpress.com, so I'm going to block that. We've got, it's called an LED strip, light individually addressable. Sounds promising. You can get black or white PCB. You can get IP30, IP65, or IP67. So lots of options. You understand what these options mean. I think you're armed and equipped to choose for yourself now. Obviously, buying in higher volumes is going to get you a better price per unit. And yeah, beyond that, you just need to give enough lead time to these suppliers so they can actually get you your materials all the way from China. You will find similar products or exactly the same products on Amazon, but they are typically enormously marked up. We're talking like 5x to 10x marked up in terms of price. So it's typically much more economical to buy from these suppliers. If we go back we'll see some other interesting options. So these strips, they come in spools, essentially. They look like strips there, but that's what they look like when they arrive. Spools. There are other formats you can buy. So this would be like an entire panel. So each of these emitters, each of these has a different chip associated with it, so a different address. So you can use that as basically a rectangular panel, pretty much like a screen. And then there are some funkier form factors like these rings. The rings are quite nice. They're very delicate, very sort of elegantly spaced. They're very beautiful. These actually come on a hard PCB, so that's another option that we haven't discussed, is essentially hard PCB versus flex PCB. Flex PCB, you can bend around corners like you see in this panel here, but the rings come on hard PCB, so something to think about. These rings are quite good for sewing into clothing, as an interesting side note. And look, there you've even got an address sequence diagram showing how the addresses snake through. We're going to get more onto exactly how the addresses work later, but if you start thinking about it, it's like this is the first LED and this is the second and this is the third, and it snakes back and forth in that type of sequence. So each LED has an address. Let's have a look at some different modules. So why don't we try to find some 12-volt modules? So you can get addressable 12-volt strips. Let's see if there's a good example of one of these. Potentially these. Nope. Potentially these. Okay, so this is a little bit nuanced, but remember how we said that in 12-volt strips, every 3 emitters will have one IC. So every 3 emitters will be controlled together as one pixel with one address. If you look here, you will see this thing, which is the IC, that is the chip. And these white squares are the emitters. So if you look closely, you'll see that every 3 of these white squares, the SMD 5050 emitters, has one IC. So that right there is a 12-volt strip. Above it, you see the same thing, but with black printed circuit board. Here you see the same thing, except at a higher pixel density, okay? So this is 30 per meter, this is 60 per meter. So you can see it's the same thing, 1, 2, 3 emitters for one chip, but they're less spaced out. Cool. And maybe we can find some even more exotic modules. So when you see things like this, there's a famous four-tet light show, which involved basically a large swarm of these units. Now, these units you can simply buy off the internet and string lots of them together. So all the artistry comes down to how you control them. The units themselves are easy to acquire. And what's going on here is exactly the same circuit fundamentally as what you see in the strips. There's a length of wire, there's some printed circuit board inside this sphere. It has some emitters on it and an address controlled by an integrated circuit. And then it passes power and signal down to the next one. So this is just the same thing, but stretched out, basically. What the sphere does is it does that diffusion, that term that we mentioned at the beginning. So the milky acrylic or plastic shell that's around the lights will essentially interrupt, disrupt, and break up the light a little bit so that it spreads out. And that's how you get a more cohesive glow coming from the entire sphere. So those are some LED module options for you to consider. All right, now time for something slightly different. So as we know, LEDs are parts of electrical circuits. They require electricity to run. How do we design and create the correct LED electrical circuit? What parts do we need? What are the considerations? Let's build up our understanding from the ground up. Okay, so introducing a couple of top-level electrical terms. Current is simply the flow of electrons from one point to another. So flow of charged particles. Okay. We don't need to go too deep into the physics of this, but for now, let's just establish some terminology. And we're going to call our current A, okay? A stands for amperage. Current is measured in amperes. And this unit is named after a physicist who worked with, maybe discovered current, I don't remember. A, when you see A, we're talking about current. Okay. Next is voltage. So voltage is essentially the potential energy carried in your electrical current. Voltage is part of the specification of how these circuits work. So typically any appliance that you work with, all the way from a dishwasher down to an LED, will have a specified voltage, and you need to provide it with precisely that voltage in order for it to operate. So we've talked about 12-volt LEDs, we've talked about 5-volt LEDs. Voltage we will represent with a V. Now, there are a couple of other terms that you want to look out for when you're working with power. There's AC and DC, alternating current versus direct current. AC is typically the type of power, without going into too much detail, it's typically the type of power that you get from your mains, from a socket, from a generator. So this is like what's coming out of the socket on the wall. LEDs and lots of, basically any microcontroller circuit will operate on DC, direct current. So in contexts where you're powering an LED installation or stage from the mains or from a generator, you will need some form of AC to DC converter, okay? When we talk about the voltage of LEDs, we're always talking about direct current, DC. Now, what is power? So power is the synthesis of current with voltage. So power is represented in watts, and the symbol is W, also named after a physicist who was studying this stuff. Okay, so you will have encountered watts on any electrical appliance you've worked with in the past. Anything you've ever seen. This is essentially a measure of how much power this appliance will consume per hour. This can be a maximum rating, so the maximum quantity of power that will be consumed in some unit time, usually an hour. But also, not only can it be a maximum, but it can be sort of like a typical range, or typical power requirements, typical power output. The main thing you need to know here is that the relationship between these different terms is current times voltage equals power. Okay, and we'll dig into some examples of this later on, but let's just do a quick example here. let's say we have a 15-watt LED appliance of some kind that we've created, and we know it runs on 5 volts. How many amps does it require? Well, 15 divided by 5 is 3. Okay, this is the type of calculation that we'll need to do in order to establish an understanding of the power requirements for the systems that we build. All right, so where do we get power from? There are 2 main sources, and it depends on your use case. The simplest source that we're very used to working with is batteries, okay? When you're making a wearable like a hat, it needs to run on batteries because you don't want to spend the entire festival plugged into the wall. The best way to do this is to just use conventional cell phone charger packs. They already run on 5 volts. They output 5 volts. They work nicely with existing form factors, like the micro USB cable. And they're getting pretty beefy these days. So they have some pretty reasonable capacity. So let's just have a quick look at what those might look like. Yeah, so this is your standard battery pack, relatively cheap. The main stat that you want to look at beyond the voltage that it outputs is this number, the mAh, a number followed by mAh. This stands for milliamp hours, okay? Higher means more capacity. Higher means the lights will be on for longer. Let's look at the math of this. So let's think about 10,000 milliamp hours. What is an amp hour? It means it's capable of providing 1 amp for an entire hour to an appliance. What's a milliamp hour? Well, that means it's capable of supplying 1,000th of an amp, 1 milliamp for 1 hour. So if we've got, let's say we've got 10,000 milliamp hours. How many amp hours is that? Well, if a milliamp hour is 1,000th of an hour, then this is 10 amp hours. Okay, so what sort of appliance would you be able to run on 10 amp hours, and how long would you be able to run it for? Let's say we had our 3 amp appliance from over here, 3 amps, and we've got 10 amp hours to work with. Well, that would be equivalent to 3.33, repeating, of course, hours. So 3 amps per hour for 3.33, repeating, of course, hours, amounts to 10 amp hours, and that will drain your entire battery pack. Okay, what's your other option? PSUs. PSU stands for power supply unit. This is another base component, another thing that's typically manufactured in China or Taiwan, and another thing that's good to get off of AliExpress or Banggood. So let's have a look at PSUs. Now, PSUs are also where this AC to DC transformation typically takes place. So if I just search LED PSU, we get this kind of thing. Okay, so this is what your conventional LED PSU looks like. And they have specifications which we may be able to interpret now that we've got the right terminology. So voltage, this is the voltage that it outputs. This needs to be exactly the same as the voltage of the LEDs that you're trying to power. It's got an amperage, 30 amps here. This is the maximum amperage, the maximum amount of current it can output. So when we're calculating how much power and which PSUs we need for our LEDs, we will need to calculate the maximum quantity of current they could ever consume or need, and then use enough power supplies to cover that maximum current. This is key for safety and the success of your circuit. You want to have more than enough total potential current to meet the needs of any appliances that are plugged in. And you should know by now, based on our math, that watts is the total power that is capable of being output by the unit. And naturally, 12 times 30 is 360. So this relationship makes sense. So this unit can output 360 watts. Okay, what goes into the unit? Let's see if we can find a diagram. So this is what you'll typically see. This is what you'll typically see when you buy one of these units, okay? So right here, you have your mains input. This will be taking AC current, AC power from your main socket or your generator. Okay, this is your neutral line, this is your live line, and this is your earth. We can explain the difference between those two in a little bit. So that's how power gets in to this transformer. And then this is your DC direct current output bus, okay? So you've got some cathodes and some anodes here. So that's the ground wire, and that's the hot wire, or the line wire, or the positive. Okay, this is what you'll use to power your LED circuit, by connecting metal to these terminals in order to complete the circuit. And all the specifications are found up here. So the input is 100 to 240 volts alternating current that supports lots of different nationalities which run their power grids on different voltages. It tells you what the output voltage is there, 5 volts, and it confirms that it's made in China, because all of these things are. Incidentally, Meanwell happens to be the brand of PSU that I've had the most success with. They're much, much more reliable than other brands. They're roughly 4 times the price of the cheapest PSUs, but they will last way more than 4 times as long. So well worth the investment to get Meanwell. Okay, so let's do one more calculation, which is the input into one of these transformers. So if we know that A times V equals W, and we live in a country that operates, let's say, 240 volts alternating current out of the mains. Now, it may not be apparent, but a typical mains socket, at least in the UK, is capable of supporting 13 amps of current. So what total power, what total wattage can we support from one mains plug in the UK? Well, 13 times 240 is 3120 watts. Now, that's why if you plug too many appliances into one socket and their total wattage, let's say you plug 4 kettles to make 4 amazing cups of tea into the same socket, they might exceed this total wattage, and then you will trigger one of your fuses on your switchboard, and that circuit will be shut off because you've exceeded this wattage maximum and thus created an unsafe circuit. Okay, so that's some of the introduction into some of these power components. All right, Let's talk about one more component and then maybe try to draw a little circuit diagram in our whiteboard. So the last component is cables. Now, cables, they just carry electricity, digital signals or power from one location to another. But their importance is not to be understated because one, in order to build a circuit, you need to know where to attach the cables. So what wire to attach where and where to attach it on the other end. Just like in the spy film, like should I cut the red wire or the blue wire? Cables, super important. But also from a design perspective, cables can be costly. They can be one of the more time-consuming elements of a project if you have to solder lots of small cables together, or even just plug lots of cables in. And so you really want, and they can also be ugly, frankly. They can be an undesirable visual component of your project. And so correctly designing cable lengths, maybe getting custom cables manufactured, or otherwise concealing the cables in your project is a really key consideration. You also want to minimize the length for electrical reasons, which we'll get into in a moment. So yeah, cables, super important. And just for the sake of extreme clarity, what a cable does is it contains an electrical conductor, typically copper, which serves to carry electricity from one location to another. And that is surrounded by an insulator made of rubber or plastic, which protects other things from touching or interfering with or getting interfered by that electrical signal, that electrical circuit or current. Okay, so when you see interesting, bizarre types of cables, just know that on a fundamental level, they're all the same thing. They're all one or multiple conductors that are insulated from one another. So if we look for, let's say, ribbon cable, this is a spool of multicolored cable. And each color is essentially a different wire, a different conductor surrounded by an insulator. Okay. When we look at, even if you look for like an HDMI cable, it's really the same thing internally. So those little pins on the end, they all correspond to an individual separate cable that's running through the length of this and mapping, connecting into one of these pins on the other side. So this is a fundamental concept in circuit design. And it's not the sexiest part, but it is really important to get it right. So if we go back to our LEDs that you can typically buy. So once again, we'll search WS2812B LED strip. We'll pull up this one. We'll have a look at the image. There are cables being considered here. You might be able to start seeing them there, but each of these strips starts with a red wire, a white wire, and a green wire, and then these connector units, which happen to be called JST connectors. Okay, and you need to know exactly what each of those wires does, and you need to have a method of connecting them into your circuit appropriately. The JST connectors standardize this, so they make it into a simple male-female plug and socket scenario, which make it very easy to chain these things together and plug them together without doing any soldering. But just know that cable management needs to be done correctly in the world of LEDs. And if we search for JST connector, you'll see that there are a number of different standardized products. So these units, these 3-pin units, come attached, pre-soldered on to the ends of your LED strips. If you wanted to, you could make up a custom cable, which is like a JST 3-ply extender, which has a male JST connector on one end, female JST connector on the other end, and 3-ply ribbon cable spanning in between of whatever length you want. Okay. So let's try to build up a circuit diagram of an LED strip using some of the knowledge that we've got now. So I'm going to draw our PSU. Let's call this PSU. Make that a little bit bigger. Power supply unit. And it's got a terminal bus on it. Okay. Very similar to the image we saw earlier. So let's make a terminal bus. Let's call this V+. So that's the hot wire or the live wire or the line wire. There's lots of different terms for this. So current flows from the V+, current flows from the cathode. We will also have an anode, so current flows to this. And then, of course, we will have the inputs to our power supply from the mains. So we're going to have line, neutral, and earth. Okay, so this line is essentially equivalent to the cathode in AC systems, and this is equivalent to the anode in AC systems, and this is essentially an existing, an additional safety mechanism which allows current to travel directly down into the physical ground of planet Earth if something breaks. Okay, so let's make another box, which is our mains generator. That's your plug. Okay, so now we want to wire this thing up right. So let's look at the international conventions for wire colors. Let's go with the UK. But disclaimer, this may not be the same for your country. Look it up, get it right, test it, use a multimeter, be safe. Let's take this diagram, okay? So we've got a multicolored green and yellow wire, that's the earth. We've got a brown wire, that's live. And we've got a blue wire, that's neutral. Okay, let's draw that in. So let's say we've got a thick, not that thick, a thick brown wire. Brown. How do you make brown? Maybe something like that. Yeah. Thick brown wire leading to line. Thick blue wire leading to neutral. And a green and yellow wire leading to earth. Okay. And this is going to be 240 volts alternating current. And let's make that nice and big. Really big, please. Okay. There's your mains. Now, let's assume we have a 5-volt output. Okay. We are going to hook up this into our LEDs to complete the circuit. Okay, so what are the correct colors? The convention is actually not typically the same for LEDs. Once you're working with low voltage, the colors change a little bit. So let's make our JST connector. And let's create some wires. So we've got a green wire. This goes to the data input, and more on the data input later. Got a positive wire, which is red. We've got a minus wire, which is either black or white. So be careful there. And just to zoom in on these symbols are meant to designate what these copper pads function as. So these copper pads are wired inside this printed circuit board into this circuitry that's inside here, that's much more nuanced and complicated than what I've drawn in this diagram. But they essentially provide a physical connection, okay? Physical electronic connection. So these are literal copper pads, which you will be able to see on the circuit board and are required to make that connection. And if you wanted to take a 1 meter strip and cut it to make it into a ½ meter strip, for instance, you could simply cut along those copper pads and then add another JST connector in. How do you add stuff in? Well, you need to solder, and we're going to get onto that in a second. Okay, so let's assume we are using the same color convention for the outputs of our PSU. We're going to have something that goes like this. And let's get it out of the way. And something that goes like this. Get it out of the way. Interactive exercise. Which of these should be which color? You have 0 seconds to guess. The answer is that the positive should be red. Okay. That's not the same color, red. So I'll keep it nice and identical. Okay, cool. So this is the makings of a rudimentary circuit to power your LEDs. Now, we haven't spoken about this green wire yet, but we will when we come to talking about control. All right. Now, some of you might be thinking, this looks like an incomplete circuit. Aren't circuits supposed to go out and around and then connect back into something? Now, it's okay to be having this thought. The circuit is a little bit complicated already. Let's clarify exactly how it works. This circuit is essentially already connected back into everything it needs to be. So there are tiny wires, tiny copper traces inside these printed circuit boards, which actually connect this negative wire all the way through to here and all the way through to here. And in addition, there are tiny copper traces that also connect this positive wire through to here and through to here. So at each junction, your current has the option to pass through this emitter, this pixel, this integrated circuit here, or carry on. And then it has the option to pass through this one or carry on. And it has the option to pass through this one or carry on. And when it passes through, then the current connects back through to this negative wire and goes back to the power supply and completes the circuit. So in essence, you can think of these LEDs as being connected in parallel, okay? It's almost as if this positive wire exists along the top and the LEDs fan out from there, and then the negative wire coalesces at the bottom. So this is already a complete circuit and it will turn on. All right, let's now get into a calculation of what our power requirements are. So what is the math that you need to do to ensure that your system is designed correctly from an electrical perspective to be safe and to get the maximum brightness out of your LEDs? Okay, so let's start by getting a power requirements estimate from a real LED product. So let's go back to AliExpress. Search for what we've already been searching for, WS2812B addressable. Look at our strips. Let's see if we can find in the specification here what the total power requirements are for one of these strips. Okay. There's some quite good information here. One LED chip, by that they mean a pixel, so one IC with one emitter, is about 0.3 watts, okay? Now, these are operating at 5 volts. So let's quickly do the exercise. One LED chip, one of these things, if one of these is 0.3 watts, and we know that it operates at 5 volts, how many amps are required per pixel? Well, the answer is 0.3 divided by 5, so 0.06 amps. Okay, 0.06 amps. We have another term for this, which we've already seen in here, milliamps. So it can be nicer to work with milliamps instead of these decibel numbers. So that would be 5 volts times 60 milliamps. 0.06 amps is equal to 60 milliamps because each one of these is equal to 1,000th of one of these. Okay, let's carry on with our analysis. So if you buy 5 meters at 60 LEDs per meter, the total LED strip is 300 LEDs. The math checks out. 5 meters times 60 LEDs per meter, 5 times 60 is 300. Each of those requires 0.3 watts. 0.3 times 300 is 90 watts. So 90 watts per 5 meter strip of these particular LEDs. So where does this amperage come from? Where does that part come from? We know that this V, this voltage, is sort of an intrinsic characteristic of the circuit. What's the deal with current? Okay, so the way these LEDs work is the more current you drive into them, the brighter they get. More current, more light. Okay, that makes sense. And now we're going to have a color theory section later, but just for now, let's dig a little bit deeper into why there's an R, a G, and a B. So in essence, you can create pretty much any color you want by combining R and G and B in different amounts. It's sort of like mixing paint, but also totally different for some fundamental reasons. So let's say we wanted to create white. How on earth can you create white from red, green, and blue? Well, it turns out that if you combine them together in equivalent quantities, so the same amount of brightness of blue with the same amount of brightness of red with the same amount of brightness of green, you will visually, as the viewer, perceive that as white. The beauty of human sight. So if we know that driving more current into each of these channels in the emitter makes them brighter, and we also know that white requires an equivalent contribution from each of the channels, then we can infer that the brightest this emitter can ever get is when all 3 of the channels are set to their maximum brightnesses, And the color that it will look like is white. So that means that roughly each of the channels in there is responsible for 1/3 of these 60 milliamps. So 20 milliamps per channel. And the reason this is listed as the wattage of the strip is that this is the maximum current that can be drawn, the maximum brightness that can be set for each channel, and essentially full brightness white is what we're going to get out of it. So whenever you see wattage or power ratings on LED assets or appliances, you can know that it's rating for when the entirety of all of the emitters are set to full brightness white. Okay. So we want to design a system which is safe if someone was to get a hold of our controls and turn all of the LEDs in the entire system to full brightness white. That is the ceiling. That is the parameter that will define how we calculate all of our power requirements. If we can do that safely, we can be certain that the system can do any other combination of colors safely, because any other color combination across any of your LEDs that isn't full brightness white will necessarily consume less power than full brightness white. All right, so 0.3 watts per pixel. Let's do a calculation. Let's say we have a system which has 2,000 of these pixels, okay? We've got 2,000, let's say 10,000. 10,000 pixels is how many watts? 0.3 times 10,000 is 3,000 watts. Okay. Now, how on earth are we going to provide 3,000 watts to our system? Let's just get a PSU that handles 3,000 watts. Okay, let's go and search for a PSU. What are the options? Let's have a look at this. It looks like they've got many different options. So if we choose 5 volts, the biggest PSU we can get is a 400 watt PSU. Isn't that quite surprising? So if we know that, if we've got this calculation, we know that we can drive up to 3,120 watts along this mains line into the PSU. We can't ever get that much wattage out of the PSU. Those units simply don't exist, and there are technical reasons why they don't. So you need to get a little bit crafty. Typically, the architecture of an LED system with lots of pixels with big power requirements is going to be split up into smaller domains. So let's build an example of what that looks like. I'll build one additional domain to show you how this stuff can multiply out. That's a little bit ambiguous. Let's make them come in at the bottom, like good little wires. Okay, so line needs to be brown. We still got brown in our palette, yes. Neutral needs to be blue. And earth needs to be greenish. So this is sort of like a prototypical example of how you would set up a many strip, many pixel LED installation. So you've got lots of different power domains, each of which is capable of, let's say, 400 watts. And we specify that the LED appliances attached into each of these PSUs will never exceed 400 watts. So let's do one final calculation. Let's see how many LEDs we're allowed to plug in to a 400 watt power supply. So let's say we've got n pixels equals 400 watts. So what is n? So since each pixel requires 0.3 watts, 400 watts divided by 0.3 watts equals 133.33333 forever. Sorry, 1,333.33, etc. Obviously, since you can't have a third of a pixel, really, we can kill that. And then it's always safe to build some safety buffer into these. So you would never want to request the absolute maximum capacity power from a power supply unit that it can support, especially for long periods of time. So it's safe to bump this down by, let's say, 100 or 133, just to add a small safety margin in. 10% safety margin is fine for a rule of thumb. Okay, so 1200 pixels supportable by each of these. All right, so in terms of calculations, we've talked about power requirements, how to make and design a safe circuit. We've talked a little bit about color and how that plays into power requirements. So full brightness white is what you're calibrating your system towards. Talked a little bit about safety margin too. So always calculate your maximum possible power requirements and subtract and add 10% on top of that to get your safe quantity of power that you need to supply, or conversely, calculate the amount of power you've got and then subtract 10% of that to get the amount of power you're allowed to use and ultimately the number of LEDs you're allowed to hook up. Now, I mentioned briefly that cable length is a factor and you want to minimize cable length when possible. This is related to a tactic called power injection, which is necessary because of a phenomenon called voltage drop. Okay, so let's dig into this a little bit. So these red and white lines, of course, are meant to represent our power cables going from our PSU into our LEDs to supply them with power. And frequently, the PSU is not going to be perfectly next to your LEDs. You may want to obscure the PSU. You may want to protect it from the rain. And the LEDs, of course, you want them front and center. You want them visible to the audience or the viewer, whoever's going to see this thing. PSU's ugly, LEDs pretty. So that means there's always going to be some distance between the PSU and the LEDs. But too much distance there is bad, okay? So there's a phenomenon called voltage drop. Essentially, whenever current is passing through a resistor or a conductor, which a wire is, some of the energy contained in that current is going to be lost to heat. This is a physics phenomenon. So not all of the energy or potential that starts out at the PSU is going to make it to the LEDs. This can be measured. So if you take a multimeter and measure the voltage over longer and longer distances of wire, you'll notice that the voltage drops. Now, we know that these LEDs need 5 volts to survive and to work. And in reality, since they're well-engineered, sophisticated electronic systems, they can tolerate a little bit of variance around that 5 volts. So it doesn't have to be, in practical reality, it doesn't have to be bang on 5 volts. I think they can operate down to something like 4.5 or maybe even 3.3. Don't quote me on that. But ultimately, it is possible that you make your cable so long that it incurs a quantity of voltage drop, which is unsustainable for your LEDs. Now, it just so happens that lower voltages are more susceptible to voltage drop per distance than higher voltages. So when designing this circuit, the ideal architecture is to have this line carrying power from your mains to your PSU as long as possible. So put the PSU near the LEDs. And this line carrying power from your PSU to your LEDs, to your load, as short as possible. Because 240 volts is less susceptible to voltage drop. And the appliances 240 volts typically run are less vulnerable to lower voltages than these low power or low voltage circuits. Now, where does power injection come in? So it just so happens that these wires inside the printed circuit board also count as cables. And for that reason, they also have the capability to incur voltage drop themselves. So that means that even in a working, functioning LED system, over a long length of LEDs, you will incur voltage drop. And you'll actually be able to see this if it's occurring, because the later and later LEDs in the chain will be less and less capable of demonstrating or showing, displaying full brightness white. So if we search voltage drop LED strip, this is a reasonable image. The near end, normal brightness, the far end, lower brightness. You get the idea. So how do we mitigate this? We use, bear with me. We use power injection. So it just so happens that, as we discussed, since these circuits are in parallel, it's completely fine to add additional wires that connect in at any point here. So you can complete this circuit again at any point, wherever you want. So typically this means figuring out the length over which voltage drop will occur and adding your wires in there. So you actually want to inject power both at the beginning and the end of your strip. Now, once again, since these are in parallel, you're not even really dependent on these power inputs here. You can inject the power wherever you want. It's completely agnostic to the location of the power injection from the perspective of crafting a valid circuit. From the perspective of voltage drop, you want sufficient power inputs into your LED strip in order to ensure the voltage drop doesn't occur. Okay, so that's voltage drop. Now let's talk about how you actually make these connections. So when things are going well, when you're on the happy path, you will always have some form of connector that you can just snap together and call it a day. On a PSU, these things get potentially a little bit more complicated, one level more complicated, and you have to use screw terminals. So this means getting the bare ends of these wires and literally screwing them down with a screwdriver into a metal plate in order to form the connection. When it comes time to do things like injecting power or connecting bare cables into these LED strips, or injecting power somewhere into these LED strips, or even taking another LED strip and splicing it in here, let's draw these. Let's draw these guys. You will need to do some soldering. So, soldering technique is something that anyone can accomplish. It is something that takes a little bit of time to master, but you can accomplish it early on. It's a physical skill. It requires dexterity. It requires knowledge of what you're doing, and it requires experience. There are plenty of guides online on how to solder. So I won't cover soldering technique in this video, but ultimately, soldering will be required. So you'll need a soldering iron, you'll need solder. Lead-free solder is preferable for health reasons. You'll need flux, which helps the solder melt. And you'll need some way of safely cleaning your soldering iron tip. So look up a guide and learn to solder. Soldering is super useful. You can also use it for fixing any like home appliance. So, and it makes you feel kind of like a boss when you solder something and it works again. Ultimately, what your objective will be when splicing LED strips together is to solder these copper pads together. Now, this is quite small soldering. These pads are quite small, which makes them more difficult to work with. So if you can get your hands on a magnifying glass, that can be very helpful. If you can get your hands on a pair of helping hands, which is a soldering appliance, which looks like this. This one's really good. So you can essentially, it's like a bunch of grippers that are positionable, and they'll hold your circuit board in place while you solder it. So a set of helping hands. That will help. And you will want to tin the pads before you attempt to adhere any wires onto them. So this means getting some solder down onto the pads, melted down onto the pads before you attempt to put the wire on. Now, I have discovered over time that the best methodology for doing this is actually to place the tip of the soldering iron underneath the pad and then hold the solder spool on top of the pad. And the soldering iron will heat up the pad from beneath and make the pad itself hot enough to melt the solder spool, which will then bead up onto this copper pad and eventually melt. So that is the pro tip for soldering LEDs together. Most of your soldering can be avoided with good project design. Okay, control engineering, another challenging section. So what is control engineering? There's a critical part of our LED circuit that we haven't discussed yet, which is the data wire. This green wire that goes into the D labeled pad. It's essentially how we tell the different LEDs what to do and when. So what color to be and when. If you think about all the LEDs in your installation as a screen, just like the computer or phone screen you're watching this on, the way a screen generates the illusion of animation and continuity in a moving image is by simply setting all of its pixels to a set of colors, and then in the next frame, setting them to another set of colors. And so you get these smooth transitions from one color to the next, which ultimately come together to make the illusion of motion and continuity. So that's what our objective is with the data wire. We want to send a signal to the integrated circuits in these pixels that tells them what color to be and when. Okay, that's what the data wire does. But what exactly does it carry? Okay, brace yourselves. It carries a digital signal which instructs each of these RGB emitters what color to be. In order to understand this digital signal, you have to understand digital signals in general. Digital signals are composed of bits, okay? So by oscillating the voltage on this wire up and down between 0 volts and 5 volts, you can essentially express zeros and ones. So 0 volts means 0 and 5 volts means 1. So you can oscillate this signal up and down. Now, zeros and ones, what's good about them? Well, they're only the informational basis of all computing. So zeros and ones can carry a lot of information. In fact, anything that can be considered information can be expressed in a sequence of zeros and ones. Let's do a quick example of how bits work. Before that, let's do a quick example of how base 10 number systems work, okay? So what's a number? Let's take the number 99. We work in the decimal number system all the time. You know what this means, but how does it get its value and how is it specified? Well, it turns out that this place, the ones place, this essentially corresponds to 10 to the power of 0. So the ones place in a base 10 number system means how many of 10 to the power of 0 do I want to represent in this number? I want 9 10 to the power of 0. What is 10 to the power of 0? Well, 10 to the power of 0 equals 1, just in case you didn't know that. The tens place corresponds to 10 to the power of 1. So this is saying how many times 10 to the power of 1 do I want? I want 9 times 10 to the power of 1. So this was times 9 equals 9. 10 to the power of 1 equals 10. And 10 times 9 equals 90. So the total represented by the numerals 99 in a base 10 number system is 9 plus 90, which is, of course, bear with me, 99. Cool. What if we wanted more? Well, the hundreds place determines how many of 10 to the power of 2 units we want. So 10 to the power of 2 is 100, and 8 times 100 is 800. So 899 is equal to 9 plus 90 plus 800. And this sequence continues for the base 10 number system. So this is 10 to the power of 0, this is 10 to the power of 1, it's 10 to the power of 2, all the way up. There's also stuff that happens after the decimal system, after the decimal point. And this is 10 to the power of -1. Now, we won't get too deeply into that. But the system, this is how a numeric system works, a number system works. So let's translate this knowledge to binary. Binary is identical to the base 10 number system, except it's base 2. So let's illustrate that. Simply change these to 2. So the first the first column is saying, how many 2 to the zeros do I want? Now, you can only have either 0 2 to the zeros or 1 2 to the zeros. Binary consists of zeros and ones. Let's say we want 1 2 to the 0. Let's do our quick math. So 2 to the 0 equals 1 times 1 equals 1. Let's say we want a 0 in this column. So 2 to the first power equals 2 times 0 equals 0. And 2 to the second power, let's say we've got one of those. 2 to the second is 4 times 1 equals 4. So this number in binary 101 essentially can be interpreted as 1 plus 0 plus 4 equals 5. So that is 5 in binary. So if you've ever seen the joke, there are 10 types of people in the world, those who understand binary and those who don't. Well, you now understand it, because 0 plus 1 unit of 2 to the first power, which is 2, which looks like 10, actually is equivalent to 2. So there are 2 types of people in the world, those who understand binary and those who don't. Let's do one more example. Let's talk about a base 16 number system. And this is getting really freaky, but it's relevant to the number theory that we'll be, the color theory that we'll be talking about later. So let's imagine this is 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. So let's say we want 9 16s to the power of 2, to the power of 0. So that's 16 to the 0 equals 1. Any number to the power of 0 equals 1. Times 9 equals 9. Now let's say we want 11 of these. Well, you can't represent 11 with a single digit, so we're going to need to come up with another digit. Let's say after 9, we move on to letters. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, and so on. So 10 would be A, and 11 would be B. If you've ever seen a hexadecimal number, you'll start to recognize this. So B represents 11. So let's say 16 times B. 16 times 11 is 176. And let's say we want a high number. So if 10 is A, 11 B, 12 C, 13 D, 14 E, 15 F. Okay. So we've got F is 15 and 16 squared is 256. So 15 times 256 is 3840. Okay, so 9 plus 176 plus 3840 is 4025. All right, so there you have the hexadecimal number system. We've learned decimal, which is our home base, learned binary, and we've learned hexadecimal. In any of these number systems with any base, it's possible to express any number. So let's dig into why this digital signal is relevant. All right, let's do even more math. So what is the digital signal content that actually gets received by each of the chips at each of these addressable pixels? Well, it turns out it is a string of binary numbers. So let's make a string of binary numbers. Now, it just so happens that these chips are 8-bit chips. What does that mean? That means you get 8 binary numbers. 1, 2, 3, 4, 1, 2, 3, 4. Okay. So that is one 8-bit binary number, also known as a byte, 8 bits to a byte. And there's 1 byte, or 8 bits, for each of these red, green, and blue channels. So let's say we've got red and a blue, which is slightly different, and a green, which is slightly different again. Let's see just how these digital binary values are used to set the color here. Okay, so let's calculate their values. These correspond ultimately to the amount of current that will flow through each LED. So you're sending a digital instruction for the integrated circuit to increase or decrease the amount of current being sent to each LED. So here we've got 1 in the ones place. So that's 1 plus 0 2s, 0 4s, 1 8, 1 plus 8 plus 16 plus no 32s plus 164. Okay, this equals the same thing, except there's no 1. So it's 8 plus 16 plus 64. This equals the same thing, except we've got the final place as well. So 1 plus 8 plus 16 plus 64 plus 2 to the 7th is 128. Okay, now let's just, for the sake of argument, figure out what the maximum possible value of a byte could be. If all of the bits were set to 1, that would be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. So 1 plus, hey, let's just copy it in, is 255. So the maximum value is 255, and that's starting from 0. So there are 256 possible values for each of these. So that means that if you can set this blue channel to any of 256 possible values, and you can set the green channel to any of 256 possible values. Let's make it explicit with colors. You can set the red channel to any of 256 possible values. You can set the green channel to any of 256 possible values. Yep, and you can set the blue channel to any 256 possible values. That equals this number. That many possible different colors can be emitted from each of your LEDs. No more, no less. It is a specific quantized amount. So if you ever heard someone say this display's got 16 million colors. Well, that's what they mean. It's an 8-bit, 1 byte per channel display. This is how the digital signal was processed. These are the physical and digital constraints of the system. Okay, so why don't we do an exercise and try to figure out what this color would actually look like if we made this combination. And let's just remove that. So it's like that. Okay, so let's tally these up and try to figure out just intuitively what this color combination would be. So 1 plus 8 plus 16 plus 64 is 89. 8 plus 16 plus 64 is 88. And this is 255 minus 128, which is 127. Okay, now the relative amounts matter because we're mixing. So let's say what we're doing here is 89 plus 88 plus 127. We know that the maximum value is 255. So let's do this in relative amounts. Let me just get my notation right here. 89 plus 88 plus 127. 89 plus 88 plus 127 is 304, but the sum doesn't really matter. The sum governs the overall brightness, but it's the mixing that matters. So let's do this in relative terms. If we really know that this is 89 out of a maximum quantity of 255, that's, let's say, 35% of the maximum brightness of red, and 88 out of 255 is also 35% of maximum brightness of green, and 127 out of 255 is almost exactly 50% of the maximum brightness of blue. So if we were to mix these together, we would get something that looks kind of like blue, but with a little bit of green and red mixed together. Now, if we use a color tool, actually, maybe we can even do it in this. Ooh, okay, so it's got hexadecimals. That'll be useful for our next example. This utility shows us exactly what we need to see. So we had RGB values, which were 89, 88, and 127. That is the color that this corresponds to, okay? And so you can see it's mostly blue with a little bit of a touch of the other colors in it too. And there are different ways to represent this number. So if you wanted to convert these binary numbers into the hexadecimal system that we saw before, let's see how that would work. So we've got 89. Let's do 89 in hexadecimal. Is 59. And you'll have to check the math of the previous section to understand this. So we've got OX59. This is going to be OX58. And 127 will be 7F. So this is the hexadecimal version of this color. So 59, 58, 7F. Now, if we look here, look, that's exactly what we encounter in the hex code, 59, 58, 7F. And indeed, if we go back into this color picker and we type in a 59, 58, 7F, we will get exactly that same color. Let's just make a square. Let's make a splotch of it. Exactly that same color that we saw here. Same color. And indeed, if we are over here and we take a color picker, also known as the eyedropper, and touch that, it will also resuscitate this color, 59, 58, 7S. So now you understand the relationship between color mixing, binary numbers that are used in digital signals, and hex values, which are used in software and web design and graphic design. This is the essence of color theory. Okay, and just one more example to discuss max brightness white. So imagine this was 100% red and 100% green, 100% blue. That's the maximum brightness each of those channels can produce. Whenever they're mixed in equivalent proportions, you will see a shade of white or a brightness of white. And this would correspond to the maximum possible values in each of the channels, which would be 255, 255, and 255. And just to run through the circuit one more time, 255 in hex is FF. So F stands for 15, 15. So we would have, we would have 15 times 16 to the 0th power, so 15, and 15 times 16 to the 1st power, so 16 times 15, and that would equal 255. So let's pick a color called FF, 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 full brightness white. You can barely see it. Cool, so that completes the circuit on color theory. Okay, now that's what the data wire carries. So you're going to be sending out a signal which has a sequence of triads of bite-sized binary numbers, 8-bit binary numbers, which govern each of the emitters in each of the LEDs in this sequence. If you happen to select APA 102Cs or any of the other related variants of integrated circuit instead of WS2812B, you will encounter another part of your circuit. Let's have a look. So what do you see? We've got our ground, which is our minus wire. We've got our 5V, which is our plus wire. We have our data, which we have just grown acquainted with. There's a fourth wire in these APA 102C circuits called the clock pin. The clock pin is essentially an additional pin or wire that propagates through this circuit. It's typically yellow. And I won't go too deep into the details of what the purpose of this is, but ultimately it is a synchronization digital signal that enables chips with a clock pin to achieve higher refresh rates, higher frame rates. So you can actually display more data, more colors, more information per second on these LED chipsets. And that means, since the refresh rate is higher, your animations will be smoother, it will be more pleasing to the eye, and it will look a lot better in video and on camera. And these chips are typically more expensive. So if you can afford to use these, use them. But they do come with that extra layer of complexity. Okay. Now let's get into control sources. Okay, so control sources is a vast subject. how do we actually generate this digital signal and send it down this wire? Typically, we're going to use something called a microcontroller. This is essentially a small computer on a circuit board. Let's draw it into our diagram. Such a gross color. This is going to have a data output. Let's get rid of our clock. It's going to have a data output which goes directly into your LEDs. Now, if you want to synchronize all of your LEDs and send cohesive data to all of them, you're also going to need to control whatever LEDs are down here from the same microcontroller, typically. There are other architectures, but this is the basic principle. So this is essentially a computer that spits out a digital signal very frequently to control your LEDs. So what are our options for this thing? Well, this is a very big subject, and typically it requires some computer programming to achieve if you're doing a custom installation. The best platform to start with here is called Arduino. This is essentially a learner's microcontroller. So let's have a quick look at this. So Arduino is essentially a very user-friendly, general purpose microcontroller board that can do all sorts of things. You can do pretty much anything you would ever want to accomplish with a microcontroller with an Arduino relatively well. So the best approach here is to buy an Arduino and look up two things. One, Adafruit. Adafruit is a wonderful LED and microcontroller and electronics, hobbyist electronics educational website, and also a store. So you will be able to download everything you need to work with Arduino, including example programs that are very easy to get started with. This is one of the best ways to learn programming, which can have enormous benefits for your life and your career, well beyond just LEDs. I would recommend that anyone tries their hand at this. It's not prohibitively expensive. You can get started for probably under $20. And if you want to get more advanced and start controlling LEDs from your Arduino, you will need to look up fast LED. So fast LED is an open source Arduino library for creating these digital signals to control LEDs and emitting them from your microcontroller. So do not be daunted. I firmly believe that anyone on this planet can learn how to program. It's one of the best and most interesting things you can do, in my opinion. And if you just buy an Arduino and try and follow the guides that you find online, you will learn very quickly and you will feel a great sense of accomplishment. So it's well beyond the scope of this presentation to teach you how to program. But as a hobbyist, some level of programming will be required to operate your LED installation. You can do it. Just look up the resources, look up the guides. They're all there. They're all free on the internet. If you've already worked with Arduino and you're looking to beef up the processing power of your microcontroller, there are additional microcontrollers. One of my favorites for wearables is called the Teensy 3.2. It runs Arduino code, but it's very small, which allows you to hide it inside headdresses and tuck it away. If you know how to use an Arduino, you will know how to use a Teensy, and in some cases can have more memory and more processing power, which you will get the benefit of by being able to run your LEDs faster and run more LEDs from a data perspective. Now, there's a totally different paradigm beyond microcontrollers, which is a totally different way to operate an LED installation. So dedicated LED controllers. And the winning brand, the industry best in class here is Advatech. And this is not suitable for a wearable piece of technology. So let's have a look at an Advatech controller. Still looks like a circuit board. Looks a little bit like an Arduino, but it's very different. This would not be suitable for a wearable. This would be suitable for a high power, many LED system that requires control from a fully fledged computer. So too many LEDs to control from a single Arduino or a single microcontroller. This is sort of the step up, the weapons grade LED control system. These are the outputs. So these 4 terminals here will correspond to your positive wire, your negative wire, your data wire, and your clock wire if one exists. You can pipe some really beefy power into this, so lots of current and a range of voltages to support different LEDs and different quantities of LEDs. And it uses this RJ45 connector, or RJ45 socket, also known as an Ethernet socket, to receive data from a computer. So you can leverage like a conventional network system with a modem or a router to distribute data across your network of these devices. So if you get to this stage, you have succeeded. Congratulations. I think it's beyond the scope of this seminar to discuss the details of this, but it helps to have Advatech in mind as where you eventually want to get to, your North Star for controlling LEDs. That's what we used in the Hooligan Alley stage, for instance. And yeah, there's also, as a side note, a large global collective of people who use these for competitive Christmas light installations in their front yards. So if you get really deep into custom LED engineering, you will likely start to rub shoulders with Christmas light enthusiasts, which is either a wonderful thing or maybe not such a wonderful thing, depending on what you like. I think they're wonderful. Okay, so let's assume that you've got an Advatech controller. Let's convert this bad boy to an Advatech controller. We're going to need another component to the system just to illustrate how this would wire in to your LED system here. Got a PC, and it's communicating over an Ethernet cable. To the Advatech controller. So now you've built a sophisticated LED system where you've got some mechanism of controlling your PC. It's spitting out instructions across Ethernet. It's getting picked up by your Advatech controller or multiple Advatech controllers across your whole installation. The Advatech controllers are spitting out a binary digital signal that's going through your data wire and getting into your LEDs and instructing them what color to be and when. And then you've got a whole separate domain of your installation, which is power supply units, which are transforming mains powers down to the correct voltage to supply your LEDs with power. Wonderful. So what's going on this PC over here? What do we actually have running on the PC to tell the Advatech controllers what to do? Remember when this was a simple microcontroller unit, like an Arduino, we needed code running on the Arduino in order to tell the pixels what to do. But if we're going to be operating from a PC, what are our options? So, time to introduce some general lighting control protocols, DMX and ArtNet or streaming ACN. Now, the details of how these protocols work are not terribly salient, because typically once you're working in the realm of a PC, you will be working with very conventional industry standard end user software, which is capable of simply detecting on a network assets like an Advotech controller, and then you simply select from a drop-down menu what communications protocol you want to use to speak to the Advotech controller, and everything is handled for you in the background. So the purpose of this talk is just to arm you with the terminology so that you can go and search and find out more about these protocols for yourself. So ultimately, DMX, ArtNet, and streaming ACN are general lighting control protocols that are found all around the industry. DMX carries a signal over a specific type of cable. ArtNet and streaming ACN are an adaptation of DMX to work over an Ethernet cable and through a network communication protocol. So typically in the modern world, you're going to be using ArtNet or streaming ACN, SACN. Okay. It just so happens that the payload of what DMX carries is very similar to this digital binary signal that we've already discussed. So understanding these binary numbers at a deep level will benefit you when you work with DMX. Okay, so if you really want to get started with a fully fledged lighting installation, a custom lighting installation using LEDs in this fashion, the cheapest and thus best way to get started is to use free and open source lighting control software. So there is an item called QLC Plus. And you can simply download it for free. It's free and cross-platform software to control DMX or analog lighting systems like moving heads, dimmers, scanners, etc. Incidentally, the purpose of these Advotech controllers is to essentially adapt custom pixel installations to work as if they were lighting fixtures, conventional lighting fixtures, alongside these commercial elements that we discussed at the very beginning of the seminar. So moving heads, dimmers, scanners, parkans, stage blinders, etc. So this is a great place to get started. Incidentally, Advotech actually has a vast quantity of documentation on their website about pixels. Here we go. This webpage, advotechlights.com knowledge base pixel protocols, is the single best webpage I've ever encountered for documenting the specifics of the different LED chipsets. So it will have our favorite WS2812B. It will show you an image of the emitter package and the pinout. It will tell you the pixel voltage. It will tell you the refresh rate. It will tell you whether there is a clock line. It will even tell you very, very detailed specifics like the spectral emission profile of each of the red, green, and blue emitters on the chip, and some easy to read advantages and disadvantages. So that should be a great place to start for understanding the different chipsets. Now we've done a lot and we're nearing the end, but I would like to show you just how deep the rabbit hole goes by adding a few more connections in to this circuit diagram in order to show how it can multiply out even further. So just to clarify a couple of things, occasionally your Advotech controller will want its own inputs from the power supply. So let's just draw those in. Make that bad boy red. And indeed, the Advotech controller can be used in itself as a power distribution system, which is very convenient because then you can use 3-ply JST connectors and pre-made cables to connect your whole installation together. Okay, so here the Advotech controller is becoming a multi-purpose node for both data signal and indeed power. Now, what if you exceed the limitations of even an Advotech controller? What can you do? Well, this entire system multiplies out. This entire system multiplies out. So what if we insert another element here, which is a router, conventional network router that you'd find in any house with Wi-Fi. And you've got an Ethernet cable coming from the PC and going into the router. And indeed, you've got an Ethernet cable coming from the router to the Advotech controller. Well, then we reach our final phase of multiplication here, where we take the whole shebang and we multiply that one more time. And of course, the mains is still powering everything down here. I'm not going to draw those cables in. It's getting a little bit ridiculous. Then you've got Ethernet going to that Advotech controller, Ethernet going to that Advotech controller. And at that point, you have almost no limitations. You can keep multiplying out this design pattern to your heart's content and build a scalable LED installation of whatever size you have budget for. And if you do that, then you can officially call yourself a custom LED engineer. Okay, the final topic. We've come a long way. The final topic are a few topics that are not explicitly LEDs themselves, but highly related to when you want to build a project. This is the structure section. So I will briefly touch on a few elements that you will need to consider. The first is structural design. So these LED strips, whatever modules you use, however you want to structure this, however you want to architect it, you're going to need a substructure to attach them to. LEDs don't simply hang in the air. So it's quite critical to think early on in the project what you're going to be attaching them to and how. I've seen and participated in some projects which were excellent in every regard other than their considerations for substructure. And I've been part of some horrific attempts to attach LEDs to materials that simply don't want to hold them. Using the glue stick, the glue strip that comes shipped on the back of these LED strips will not get you anywhere. That has never worked for anyone in any context. You need mechanical fixtures in order to hold LEDs permanently onto any sort of structure. So cable ties are very, very useful. I've seen some success with using drying silicon caulk, like you would use for bathroom tiles, to adhere pixel strips to a substructure. But ultimately, you're going to want some sort of bar or beam or wood plank or aluminum channel to adhere these things to. Let's just make that loud and clear. Loud and clear. Structure. And if we just quickly review our wonderful Radialumia by Foldhouse, you can see that what draws your attention is, of course, the wonderful LED lights. But a key element of the design is in fact this substructure underneath. So you can see these probably steel bars holding this geodesic dome together. Gotta have structure. Okay. Durability. Now, this relates heavily to structure, but it must be said that these LED strips are not vastly durable by themselves. They're floppy. If you kink them, if you twist them, if you bend them too much, if you crush them, they will break, and this will break the circuit, and this will mean the LEDs don't light up. You can attempt to repair them, you can attempt to cut them out and solder them back together, but ultimately that's a lot of work. So the best thing is to think about durability at the beginning of your project. So an example of durability, let's go back to our initial video. We can zoom in on one of these. It's almost impossible to see, but in each of these bars, we encased the LED strip that's inside there in a cylindrical plastic tube. And this means that even if someone accidentally punches one or gets crushed while we're putting it up, there will be no force exerted on the LED strip itself. So the circuitry will remain intact. And it's, as I said, it's really, really hard to ever erect the same LED installation twice because of durability issues. Obviously, this thing can be quite a costly endeavor. And so in the long run, you'll get return on investment if you think about durability upfront. And closely related is portability. So if you're working at a festival, typically you're not going to be as close to normal civilization as you would like. There are logistical problems. How do you get all this physical material into a remote location in a manner that allows you to work with it easily? How do you transport it there without damaging any of the LEDs en route? We took portability heavily into account when designing this stage. So ultimately, we designed a structural LED bar. So we've got structure, we've got durability, we've got portability, all thought of in advance as part of the design process. Each of these edges of each hexagon is a structural LED bar made of aluminum channel housing an LED strip with a plastic cover around it and standardized waterproof connectors on each end. So they can simply be bolted together. When we deconstruct this installation, this stage, we can simply flat pack them all into flight cases, standardized flight cases, and wheel them into the back of a van. So portability, durability, and structure go hand in hand. And the final element that I would like to introduce is diffusion. So we've talked about diffusion a few times. You've seen a few examples. It's using material to break up the light and give it a more milky and fluid appearance. Diffusion actually comes hand in hand with structural design, durability, and portability, because one of the best ways to make your lights more durable is to put a diffuser around them. So the plastic tube that I mentioned is essentially also functioning as a diffuser. And that's how you get these really smooth gradients as the lights oscillate from one color to the next. It looks like they're blending together. Brilliant. So that brings us to the conclusion of this long and detailed seminar. I hope you have gained some knowledge. I hope you've been inspired to make an attempt at this hobby. I believe anyone can do it, but I think that the theory can only take you so far, and the best way to learn is to buy some kit, get to the soldering bench, start figuring it out, start learning. I believe in you. Good luck.